Here are some notes over vectors. You either have this in your packet already, or you just jot all these notes down and these examples and formulas down on a blank sheet of paper. That way you're using to help you with the worksheets here. But a vector, you use these a lot in physics. You know, it's represented by array. It gives you both a magnitude and a direction. So it'll tell you like how far you're going or how far you're going to push something for the magnitude, and then it'll tell you which direction that you're pushing it at, so you know where you're going to end up, right? And so usually we just put a little arrow type of thing over there to represent vector A. We'll learn how to find a component form of a vector. To find a component form of a vector, it's just the ending point minus the beginning point, or also called the terminal point minus the initial point there. And what that will do, because you can have a vector start way up here or way down here and go in all different directions. What the component form will give us is a vector that always starts at the origin and then goes however that magnitude and direction is going to be. So we'll show you that in a second with an example. The magnitude of the vector is just the length of that vector, just how long is that vector, how far is something going to go, how far are we going to push something. And if you think about it, if you have this a comma b, that's like your x value and your y value, that's your horizontal component and your vertical component. So we would start there, we would go to the right a, up b, and if I say find the magnitude of that vector or the length of that vector, all you're going to do is just do your Pythagorean theorem. That's a right triangle. That's a hypotenuse of that right triangle. So you're just doing your Pythagorean theorem. So you don't even need a picture for these. If you have a vector in component form, if I tell you to find the length or the magnitude of that vector, it's just the square root of that, the a squared plus the b squared. So we're going to have that down. This is the notation used to represent the magnitude of the vector. It's either this notation or also what I see a lot of at like Calc 3 level and physics level is just like they'll use one bar sometimes to represent that. So if you see these absolute value type of bar type of deal, that means find the magnitude or length of that vector. To find the direction, that's when we want to find the angle. And we already know how to do this. You did a lot of problems where you're drawing triangles and you're finding the angles. And the angles for the direction of the vector, that's going to be from the positive x-axis. So I would want to know, like, what is this little angle up here? If I'm in quadrant 2, I want the quadrant 2 angle and adjust accordingly. A lot of times, you could use SOHCAHTOA for the angles for the direction of the vectors, but a lot of times we'll have the vector in component form, so we'll have this x and y, or that's a and b value. And so what we usually use is that tangent of theta right there, because we already will have those, and we don't even need a picture for these sometimes there. But I'm just going to mention that's tangent of theta. You're used to tangent of theta being like the y variable over the x variable from a long time ago. So that's kind of like the y coordinate and the x coordinate, or the vertical component or the horizontal component. And so it's just going to be like b over a. So I know some of that is a little fuzzy to you until we put that into an actual example, and you're going to see how easy some of this stuff actually is, right? So I give you 2 points here, and I want to find the component form of a vector. So we have a vector that's going to start at this point P, and it's going to draw an arrow to that point Q. And I'll draw a picture for you and show you exactly what you're finding in a second, but we don't need to draw the picture for these. If you want the component form, it's just the ending point minus the beginning point. So your ending point is the Q, your beginning point, your initial point is the P. So if I go N minus the beginning, that means I'm going to go Q minus P. So to get my horizontal component of this vector, I'm just going to subtract the X value. So I'm going to go -4 minus 3. And to get the vertical component, I'm going to subtract the Y coordinates. So I'm going to take the ending point minus the beginning point. I'm going to go 3 minus 8. And then it's just doing basic arithmetic, being careful with my numbers here. So -4 minus 3 is going to give us a -7, and then 3 minus 8 is going to give us a -5, and that's it. That's how you find a component form. You're just going to subtract some numbers, okay? Now let me review with you what you just figured out, in case you were curious. What is component form? If you plot both of those points right there, like there's point P starting at the point 3, 8, there's point Q starting at the point -4, 3. And notice to get from the initial point to the ending point, we went to the left 7, down 5, right? Now what the component form does, it gives us, hey, I went to the left 7, down 5, because this is how far you're going to go horizontally. This is how far you're going to go vertically. What the component form always gives you are those horizontal vertical components. It says we went to the left 7, and then we went down 5. So left 7 is -7, down 5 is -5. And see what this is, component form always places your vector, starts at the origin, right? So if I give you this vector in component form, that means if you start at the origin, you go to the left 7, down 5, that puts you right there. Notice that these things right here, they go both in the same direction and they have the same exact magnitude. So essentially it's like the same vector, just in a different spot, but it goes in the same direction, has the same magnitude. That's what component form is. And so that's what you found when you got that -7, -5. Now, when I want the magnitude of this vector, I want to know what is the length of that hypotenuse. That's a right triangle, which is the same thing as what is the length of this hypotenuse. I notice that this was 7 units here. This was 5 units here. So you could just use your Pythagorean theorem. You can go 5 squared plus 7 squared equals c squared, or r squared, whatever you want to call that. And then you're going to square root both sides. So that's what I give you in this formula. So if you ever forget, it's just your Pythagorean theorem. And then so we're going to, on this problem, we're going to go to the square root. This is my a right here. This is my b. That's the vector in component form. And so you're going to do the square root of that -7 squared plus the -5 squared, right? Put those in parentheses if you're plugging those into the calculator. When you square something, it's always positive, but that's just going to be 49 plus 25. And we should be able to get the exact values for these things instead of just a decimal answer. This is going to turn into the square root of 84, which we know is going to be 4 times 21. So if you do the square root of 4, that's going to be 2. That comes out of the radical, and then the 21 is still inside the radical. So be able to get the exact answers for those at simplest radical form. If we ever ask you for the decimal answer, we could always plug that into the calculator and get the decimal answer after that. But all that is, the magnitude of that vector is just the length of that hypotenuse right there. It's just that using that easy formula, find the length of that hypotenuse. And then let's talk about the thing that kind of gives some people some trouble sometimes. You got to make sure you adjust for which quadrant you're in when you give me the directions. Like if you're in quadrant 2, quadrant 3, we're kind of used to doing those. But here's what we're going on. So if you take this vector, this -7, -5, now I'm going to draw a picture typically for the direction. So -7, -5, that's that vector right there. That's going to be in that third quadrant. We've done a lot of problems with the trig stuff where we're drawing the triangles. So this is my vector. I went left 7, down 5. So I'm going to draw my triangle. I went left 7, down 5. Now remember, I always put the positive sides for the length of the triangle, and then we could use the all Snickers taste chocolatey or the all students take calculus to adjust where my stuff is going to be depending on the quadrant there. So what we can use is I'm going to find this angle right here. And then what I ultimately want to obtain is the angle from the positive x-axis all the way around. But see, I can use basic SOHCAHTOA to find that little angle, and I can go 180 plus that, and then depending on where we're at to find out my direction right there. So that's why I gave you some little tips right here. You're going to draw the component form, which is what I did. Now we're going to use SOHCAHTOA to find what this reference angle is going to be. Now, as I look at that angle, that's the opposite side, that's the adjacent side, and that's why we mentioned you can use the tangent right there. So I can go tangent of that alpha equals the opposite over the adjacent side, the 5/7. And notice what I gave you up here. I said b over a. There's the b, there's the a. And then so that's what I use. But I always just use the positive things because when we get the reference angle, it'll give me that reference angle for sure if I just use the positives. And then so to find this missing angle, remember, if you don't know the angle, that's where we're going to use the tangent inverse button in the calculator. So tangent inverse of 5/7, when you plug that in, hit the second tangent button, get that tangent inverse in there, that's going to give us 35.5 degrees. Now that is not your direction. If I'm in quadrant 1, then I'm good, all right? But see, what we ultimately need to find, your direction is always from your normal standard position, that positive x-axis, like we're used to measuring angles. I want to know what is this angle all the way around. So if I know if I go from here to here, if I stop right here, that's 180 degrees, but I went an additional 35.5 degrees. So my actual direction, I'll call that theta all the time. That my actual direction is going to be 180 degrees plus that 35.5 degrees right there. And then that's going to give us 215.5 degrees. That's how you obtain that direction. So that you just got to be careful what quadrant you're in. And so really you're just kind of applying the point, -7, -5, doing your triangle like normal. If I'm in quadrant 2, I would have did 180 minus that reference angle. If I'm in quadrant 4, then I'm going to do 360 minus the reference angle, and I'm going to come up with that. Notice how I'm in quadrant 3, and we found a quadrant 3 angle right there. So I know exactly how far out we're going, and I know exactly which direction we're going at, so I can end up at that exact spot right there. So there's the component form, magnitude, and the direction. There's a huge chunk of it right there. And then the next thing we'll talk about, I think, is pretty darn simple. Okay, I already have these filled in for you. So when you do operations just adding vectors, subtracting vectors, and doing some multiplication and stuff that we're talking about. But the resultant vector is just a vector obtained from, adding vectors or, multiplying vectors and stuff like that, right? And so if you're adding vectors, all you have to do is add the horizontal components or the x's, and then add the vertical components or the y. So I just go a plus c or b plus d. Same thing with subtraction, just subtract the horizontal ones or subtract your x's, and then go b minus d, subtract the y's or the vertical components right there, and you're gonna have your new vectors, okay? And so we'll show you examples with this in a second. Now, a scalar, what we call a scalar, that means it's just a number. If you take the number like 5 or 4 or whatever number you want and put it in front of that vector, all you do when you do scalar multiplication, you just times both of the numbers by that. So if this is a 5, it's like I'll just take a 5 and distribute that. So I'll have a 5a and a 5b right there, and then we can do those with numbers in a second. Now, there's something brand new way of doing things here. So I think these 3 operations are going to be pretty simple. You're just adding, subtracting, and multiplying some numbers together. When you do this thing called a dot product, there's a couple different uses of this dot product, but here's the pattern how it's going to work. You're going to go a times c plus b times d. This is when you're multiplying 2 vectors together. You're going to go a times c plus b times d. That's the pattern right there. So if I show you an example of that real quick, if I make up a couple vectors, I'm going to make up 3, 2. I'm going to do a dot product. I'm going to go 4 times -7. And if I want to do a dot product with those, so I'm going to go 3 times 4. I'll write that down. I'll go 3 times 4 plus 2 times -7. And then you just get a number for this. When you do a dot product, you're always going to get a number, a scalar, not a vector, but you'll get a number. So this is just going to be 12. This is going to be a -14. So 12 minus 14, that'll give us -2 for that dot product right there. So as we go to the other side of the notes, let's do some examples here. Here I give you a few different vectors, right? And then we're just going to practice the operations right there. And I already have a few of these filled in for you because I didn't think you needed that many examples, but we'll talk about those. But we'll do a few of these from scratch. So when I go r plus t, so you're just going to take that vector r, which is 4, 6, and we're going to add the vector t, which is 3, -2. And so when you're adding vectors, you're just going to subtract the horizontal components, or think of that like you're adding the x's, and you're going to subtract the vertical components, think of that as you're adding the y. So you're going to go 4 plus the 3, that's going to give us 7. And then 6 plus the -2, that'll give us a +4. And that's it. That's all you have to do there. So you're just, as long as you be careful with your arithmetic there, we should have all these right, easy problems. And then so s minus r. So I'm going to take the vector s, which is 12, 8. And we're going to subtract out the vector r, which is 4, 6. And you're just going to subtract your horizontal components. So I'm going to go 12 minus 4 to get my first number. That's going to give us 8. And I'm going to go 8 minus 6 to get that second number. And that's how you subtract the vectors right there. This letter C, you had a 2 in front. That's scalar multiplication. So I'll take 2 times that vector t minus the vector s, right? So when you have a number in front like that, all you do is just distribute that number through your vector. So I'll go 2 times 3, make that 6, 2 times -2, make that -4. And now you have that vector minus that vector s. So 6 minus the 12 is -6, and then -4 minus the 8 will give us -12. There you go. And let's do a couple more examples of this dot product. So I'm going to have vector r dot product with vector t. So I'm going to go 4 6. And I like to write down the vectors. I know sometimes these you don't need to write down the vectors. You could just add and subtract them in your head. For whatever reason, the dot product, I kind of like to write those down. Make sure I'm really careful with all my arithmetic and stuff there. So I got 4, 6, dot product that with this vector 3, -2. So remember, when you do a dot product, you'll see that little dot right there that signify we're going to do a dot product. You're going to go 4 times 3. So I'll write that down for the first example. So I'm going to go 4 times 3. So you're going to multiply the horizontal components together, or the x's together, and then you're going to go plus, and then you're going to go 6 times is -2. So you're going to multiply the vertical components together, or like your y values together. So this would be 12 plus a negative 12, and then 12 plus a negative 12, that will give us 0 for that dot product. When you do a dot product, you're always going to get a single number for the dot product right there. And then here we'll go S with the dot product of t. So I'll go 12, 8. And then we're going to go 3, negative 2. So there's my two vectors that I'm using, and I'm going to do the dot product. So I'm not going to write this down this time. I'm going to go 12 times 3. Use your calculator if you need to there, but that's an easy multiplication. So I go 12 times 3, which is 36. Write that down. Now I'll go plus. Now I'm going to go 8 times negative 2, which is a negative 16. And I go 36 plus a negative 16. That's the same thing as 36 minus the 16, which will give us a positive 20 for that dot product. All right, and so since I already gave you like 3 examples of the dot product, I just have this one already filled in for you. Notice I'm just going to go 4 times 12 plus 6 times 8. Careful with your arithmetic, you're going to get 96 for that. Now, there's a few different uses for the dot product. We're going to learn some now. We're going to learn some in the next section of the video notes there. But another word to mean perpendicular is this word orthogonal. There's 3 words in math that mean perpendicular that I know of. One is perpendicular. That means they're going to cross at 90 degrees, right? Orthogonal also means the same thing. It means they're perpendicular, so they're going to cross at 90 degrees. And then the word normal is used a lot as well, like as you take more math there. So they use orthogonal for vectors, perpendicular for lines. It seems like when you have 2 different planes that are crossing, they like the word use the word normal, like in the multivariable calculus and stuff there. But here's what we're gonna use a dot product for in this section, is we can use it to find the angle between the 2 vectors. Like in the next section of video notes there, I'll give you a vector there and then a vector there. And if I want to find the angle between those 2 vectors, that's what I'll show you in the next set of notes here. But right now, we're going to use it to tell if vectors are orthogonal or not, if they're perpendicular or not. So I want to know, like, if I have a vector like that and I have a vector like that, I can show you how to tell for sure, is that really going to be orthogonal vectors? Is that really going to be perpendicular? Is that really going to be 90 degrees there? So here's a theorem. It just says 2 vectors are orthogonal if and only if the dot product is equal to 0. So all you have to do, if I say determine if vectors are orthogonal, you're going to do what you did up here. If you get 0, like we did on this one, yes, those 2 vectors would be orthogonal. They would intersect at 90-degree angles. If you don't get 0 for the dot product, that means no, those 2 vectors are not orthogonal. They're not going to cross at 90 degrees. It's a really simple thing, but you just want to take some good notes, get the formulas down, and when you look at the directions, just know what you're supposed to do, how you're supposed to approach that. So when I say that word orthogonal in my directions, I know I'm going to be doing the dot product right here. So I got one of these filled in for you already. Let's do one together. So if I want to determine if vectors are orthogonal, I'm going to do the dot product. So if I do the dot product, so I'll go A dot B. So I'm going to go 3 times 16. That's going to be 48 plus, then I'm going to go negative 8 times 6, which is a negative 48. So if you want me to write down, it says I did 3 times 16 plus negative 8 times 6. I'm doing exactly what I showed you on these 3 examples up here. Do your dot product, get a number for that. 48 plus a negative 48 gives me 0. And then since I got 0 for that dot product, that means yes, those vectors are perpendicular to each other. Those vectors are orthogonal to each other. So I put yes, these vectors are orthogonal. So it's typically a yes or no answer, but that just means those vectors will be perpendicular to each other. So if you jotted those vectors down, like if I did this point 3, negative 8 would be over here, and the point 16, 6 would be over here. You know, you got like a vector there and a vector there. You know, I didn't draw that all that great, but that angle right there is 9 degrees if you get that dot product is equal to 0. All right, so you don't want to draw a picture though, because you see how funky that looks. You know, you're not sure. It might be 89.9 degrees there. If you do that dot product and you get 0, then that, you know, for sure they're going to be orthogonal to each other. And here's another example. If I ask you, are these 2 vectors orthogonal or not? Just simply do the dot product. This time I got 1. I did not get 0. So no, those vectors are not orthogonal to each other. Now, if we know that property, what we're going to give you here, make you think a little bit there. We're going to give you 2 vectors, but see, we're not really going to give you the full 2 vectors. I want to find this x value right here. It says find the exact value of x that makes these 2 vectors orthogonal. And here's what I'm going to do. I'm just going to do my dot product. It'll have an x in there, but that's okay. I'm going to do my dot product, and I'm going to set that equal to 0. because that's what this little theorem says. So when I do my dot product, I'm going to go 3 times x, that's 3x, and I'll go plus 5 times 4. All right, so usually I just write that down right away. I'll write down like 3x, I'll go 3 times x, which is 3x, I go 5 times 4, which is 20. That's the dot product between those two vectors. And see, if you're gonna force these two vectors to be orthogonal, you need that dot product. You need that 3x plus 20 to be equal to 0. And so it's a real simple thing. Use your easy dot product formula, go 3 times x plus 5 times 4, set it equal to 0, and then you solve this equation for the x. So you'll get 3x is equal to 20. I'm sorry, negative 20, and then divide both sides by the 3. You're going to get x equals negative 20 over 3, and then you're done there. The last thing we got to talk about, it's kind of just a weird formula. There's different projections and stuff you do, so I'm not sure if I understand exactly what we're finding here. I'll try to explain this a little bit more detail, like in class or during our Zoom meeting. But when this little formula right here, I will tell you, this is a pretty darn simple formula to work with. But it says vector component, it's going to say find the component of A along B. And it'll say this notation right here. That's a component of A along B. And we just need to have this formula memorized right there. And it's a really simple calculation, but it's just going to find a vector along a different vector. And I'll try to explain that a little bit better in class or during our Zoom meeting and what that actually is there. But I do say, even if you don't understand it, it's a really simple calculation right here. Okay, so here's what I'm going to have you do. I'm going to give you 2 vectors, and I'll say find the exact value of this notation here. So when I see that notation, that's what tells me I'm using this formula. I'm going to do the component of A along B. And so it's easy to remember. You always do the dot product on the top, and then whatever your bottom vector is, say like that little bottom part, that's what you do the magnitude of on the bottom. Okay, and so if I were to switch those around, I had the B up here and the A down here, then I just put the magnitude of A on the bottom, but I still have that dot product of A times B on the top. So part of this are already filled up for you because we already reviewed how to do this earlier in the notes. But what you need, if you're going to see that symbol, you need the dot product. So I did that here. So I did 6 times negative 2 plus 4 times 2, got negative 4 for the dot product. And then you need to get the magnitude of that bottom vector. So I need to do the magnitude of vector B. And remember, the magnitude is just the square root of A squared plus B squared. So you're working with this vector, you're going to do the square root of that thing squared plus that thing squared. That's going to give you the square root of 8, which is 2 radical 2. And then when you do this little formula, you're just going to plug them in there and then be careful with that. So the dot product is the negative 4 that we calculated. And then your magnitude of that B is that 2 radical 2. And so all this is just 2 easier problems, and then plug it into that formula right there. And then so this is going to be negative 4 divided by negative 2 is a negative 2 over square root of 2. And then you guys know how to rationalize that to get rid of the radical on the bottom. So if you rationalize it, you're going to get negative 2 radical 2. Remember, radical 2 times radical 2 is a 2. Those will cancel out. And then you're going to get negative radical 2 for that final answer right there. Okay, so that's called like a component of A along B. And we could talk about that more when we go through questions at some point. But hopefully all that helps for your worksheet there.